All right, this is going to be note card 5. It says limits to infinity analytically. So basically what we're trying to find the horizontal asymptotes without having to plug them into a graphing calculator. So if we have rational, okay, rational just means fraction, okay, fraction functions. If the degree of the numerator equals the degree of the denominator, then the limit is the ratio of the coefficients of the highest degree. So what we remember, the acronym we remember is BETC. So when the bottom equals the top, we look at the coefficients. Okay, BETC. All right, when the bottom equals the top, we look at the coefficients. So as an example there, let's say you have 2x cubed plus 4x squared minus 6 over 7x cubed minus 5. Okay, so that's an example of that. Because the numerator has a degree of 3, because that's the highest power on the polynomial. The degree of the denominator is also 3. So there, that's an example of when the bottom equals the top. When we say equals the top, we're talking about the degrees. And when that's true, this stuff doesn't really matter. The stuff after it doesn't matter. The stuff after this doesn't matter. Just the highest power term. So when that's true, all we do is we look at the coefficients. So there, the limit or the horizontal asymptote would occur at 2/7. All right. So part B. If the degree of the numerator is less than the degree of the denominator, then the limit simply equals 0. And what we remember there is BOBO. If it's bigger on bottom, then it's 0. Okay, so for example, if you have something like x minus 4 over 3x squared, okay, the power in the numerator, the degree is the first. 1 is less than 2. Right. And because 1 is less than 2, it's bigger on bottom. The degree is bigger on bottom. So in that case, the limit as x approaches infinity or negative infinity would simply be 0. Okay. And part C, if the degree of the numerator is greater than the degree of the denominator, then the limit does not exist. And the way we remember that is BO2. If it's bigger on top, then the limit's undefined or does not exist. Okay, so remember BO2. So BETC, BOBO, BO2. So an example of that one would be like 3x to the fourth over 5 minus 2x squared. Okay, the degree of the numerator is 4. The degree of the denominator is 2 because that's actually the highest power on the variable. Okay, so that is bigger than that. So it's simply the limit does not exist. All right, now for other types of functions, you have to think about what their graphs look like. So if you think about logarithmic graphs, or logarithmic functions, okay, such as y equals ln of x, or y equals log with a certain base, I don't even care what the base is, log base 5 of x, those graphs generally look like that. So as you go further out to the right, it increases, but it increases slowly. Okay. For polynomial graphs, such as polynomials or polynomial functions or polynomial graphs, maybe something like that, y equals x. It's a simple line. Or y equals x squared. That's a basic parabola. Or y equals x cubed. That does one of these things. Okay. So as you can see, no matter which one you get, it looks like it's going up quicker than that. All right. And exponential functions go up real quick. Okay, such as like y equals e to the x, or y equals 2 raised to the x, or y equals 3 raised to the x. All of those go up really quick, exponential growth. Just be careful that it's not to a negative x power, like y equals e to the negative x power. That's going to go something like that. Okay, it's going to be a decreasing function. So just be careful on that. But generally, logs go up slower than polynomials, and polynomials go up slower than exponentials. Okay. That's why they put this in here. Log graphs increase slower than polynomials, and polynomials increase slower than exponentials. Okay. So let's try some of these problems. All right. And there is no packet with this note card. So number 1, find the limit as n approaches infinity. So again, we're looking, this is like keyword for find the horizontal asymptote. So here, the power in the numerator is 2. That's the degree of the numerator. The degree of the numerator is the second. The degree in the denominator, the highest power on the end, is also 2. So here, the bottom power equals the top power. This is an example of Betsy. So when it's Betsy, when the bottom equals the top, when the degrees equal each other, then all we have to do is look at the coefficients. The coefficient of the numerator is 4. The coefficient of the denominator is 1. So this is simply going to be 4 over 1, which equals 4. That would be the limit. It's really that easy. Okay, now let's do number 2. Or I guess that's part A. The limit is 4, and guess what? That's part A. Now, what would be the equation of the horizontal asymptote? Since it's horizontal line, it would just be y equals that number. Y equals 4. And number 2 here, the degree of the highest power in the numerator is 1. The degree in the denominator of the highest power is 2. Here it's bigger on bottom. So this is an example of Bobo. It's bigger on bottom. So when it's bigger on bottom, the limit's going to equal 0. And therefore the horizontal asymptote will be the equation of the line y equals 0. Alright, and let's do number 3. The highest power of x in the numerator is 5. The highest power of x in the denominator is 2. So here it's bigger on top. When it's bigger on top, then the limit's undefined. So we would say the limit does not exist. Okay. Limit does not exist. If you actually start plugging in some numbers, okay, you actually want to think about this graph. When x is really big, like 1,000, 1,000 to the 5th power is a huge number. 1,000 squared is still a pretty big number, but it's not as big as 1,000 to the 5th. But when you take this 1,000 and square it, and then multiply by -5, this denominator will equal something that's big but negative. This is going to equal something bigger, but it's going to be positive. So the top part is going to go up quicker than the bottom because of the 5th power versus the 2nd, but it's going to be a positive over a negative number. So this is actually going to go down towards negative infinity, but negative infinity is not a number. So we might even write something like that. Negative infinity does not exist. So since the limit does not exist, there's no horizontal asymptote. There's no horizontal asymptote. And let me just, I'm going to plug that into my calculator, even though this isn't a calculator question, just so you can kind of see what I'm talking about here. So I'm going to set up the rational function, 2x to the 5th minus 7 over negative 5x squared plus 9. So the minus 7 and the plus 9 at the ends of these things don't matter. Okay. Zoom in a little bit. Now I'm going to just go zoom standard. See, as you go further and further out to the right, imagine this part of the function kind of does one of these, but then what happens here? It keeps going down and down and down and down and down. It'll keep going down forever. Okay, so as you go further to the right, if you follow this curve all the way, it goes all the way down towards negative infinity. Okay, here it is, and it's going to keep going down and down and down and down and down. So there's no magical horizontal line there. Now let's look at number 4. In the numerator, this is some sort of polynomial. Okay, it's like x to the 4th power, but they're using n's instead of x's. No big deal. Okay, so this is a polynomial in the numerator. But in the denominator, this is an exponential. Okay, so go up here. Polynomials go up slower than exponentials. Okay, so since this goes up quicker than this is an example of bigger on bottom. So when it's bigger on bottom, we use Bobo. So the limit there is going to be 0. And the equation of the horizontal asymptote will be y equals 0. Okay, just to give you a look at it, let's plug that one in. Now it's not going to look like that at the beginning. I'm just giving you warning here. And I can't use n's, but I can use x's instead. So if I do a zoom standard to begin with, you're not going to believe me. It might not even graph on a standard 10 by 10. Okay, not that good. It just gave me a part of the graph. So like at 0, it's up at 500. We can't even see it. All right, but if I zoom out a little bit, let's just zoom out so you can kind of see what happens as you go towards infinity. Okay, if you zoom out, you can see the behavior of this function as you go further and further out towards positive infinity. Okay, as you go further and further out toward positive infinity, it's getting really close to the x-axis, so it will be approaching 0. Or you can even set up a table. Okay, maybe we start at 100 and go up by tens. Okay, look at all these values. Really tiny with scientific notation. Move that decimal point 44 places to the left, and that's a value getting closer and closer and closer to 0. Okay, really small. All right. Now number 5 is a little bit complicated. Okay. What about this one? This is not a rational function. This is some sort of exponential function. Think about what would happen if you plug in negative infinity right there. So let's just kind of think about it. We would have 6 raised to the 1 over negative infinity. Okay. All right. So in this particular one, you have 1 over a really big number. Okay, so maybe like 1 over a million. That makes this thing really small. Okay, 6 to a really small negative exponent. Okay. Now if I want to rethink about that, if you have like a negative exponent, if you have like 5 to the negative first power, let me just write it up here, that's like 1 over 5 to the positive first power. So you can rewrite it. So that's like 1 over 6 to a really small positive exponent. Okay. Well, if you take 6 and raise it to something really small, like 0.001, let's see what that would be. Okay? If you do 1 over 6 to a really small positive exponent like 0.000001. Okay? What do you notice there? Okay, or if this is really small, another way to think about it, 6 raised to something that's really small, that's positive, is almost like 1 over 6 to the 0. Okay? And anything to the 0 with power, is going to be 1. So that's like 1 over 1. That's why that limit is 1. Okay? Let's actually graph it so you can understand that. So let's say I do 6 raised to the 1 over x. Let's just start with zoom standard. So that's what that graph looks like. Now it's asking what's happening as I'm approaching negative infinity, going out here. So if I trace and go out, I go further and further and further to the left. Okay, what are these y values doing? Well, there's some decimal, they're getting a little bit bigger. Maybe it'd be easier to look at it from a table. Maybe we start at 0 and we go down by -5 each time. And then look at the table. Okay, what's happening here to these y values? The further and further you go out to the left, towards negative infinity. Looks like all these numbers are getting closer and closer and closer to 1. Okay, and this is the logic that I use to get there. A really small positive exponent is almost like 0. Okay, so it's almost equal to that. And 6 to the 0 is 1. Okay. So the further we go out here, these values are getting closer and closer and closer to 1, a y value of 1. So 1 is the horizontal asymptote there. And it's also the same thing going out to the right, towards positive infinity, for the same reasons. If you think about it, if this was positive infinity, it would just be 6 over, or this would be positive infinity, 1 over a really big number. This thing's almost 0. Okay, that's almost 0, and 6 to the 0 is 1. So on both sides. So the equation of the horizontal line, the horizontal asymptote, is simply y equals 1, excuse me. It should be a 1. Number 6, that was a former AP question. It says, if the graph of y equals of this rational function has an HA at 2, what does that mean? That means the limit as x approaches infinity of this thing, ax plus b over x plus c, would equal 2. Well, this is a number. Okay. So when it's a number, we look at coefficients. So this would be an example of Betsy. And you should also notice they both have the power of 1. Okay. So this is definitely an example of Betsy. All right. So the coefficient in front of that, x to the first, is an understood 1. So a over 1 has to equal 2. Well, what's the only way for that to work? The only way for that to work is if a equals 2 by itself. All right. And they also tell us that it has a vertical asymptote at x equals -3. Okay, so what does that mean? That means that in the denominator, if I plug in -3 for x, it's got to make the denominator 0. So how are you going to figure out what c is there? Because this said x plus c. We have to set x plus c equal to 0, but they told me what x equals as the vertical asymptote. The only way to get that to work is to add 3 to both sides. So here, c would have to equal 3. If you think about it, if x plus 3 was the denominator, then -3 would be the vertical asymptote. Okay. So if A is 2 and C is 3, the question is asking me what's A plus C? Well, what's 2 plus 3? Hopefully it's pretty straightforward. The answer to that question is simply 5. All right, let's look at the next one. It says for x is greater than 0, so for positive x values, the horizontal line y equals 2 is an asymptote. Well, what kind of line is this? Y equals 2. Hopefully you recognize y equals 2 is some sort of horizontal line. So that's an HA. Okay. And an HA, if the horizontal asymptote's 2, just like before, that's an example of Betsy. Okay. All right. It says, which of the following statements below must be true? Well, does f of 0 have to equal 2? Does that have to be there? No, that doesn't have to be there. All that has to happen is I'm going to the right or as I'm going to the left. It just has to approach 2. So that doesn't have to be true. All right. Here they're saying the y values can never equal 2. Well, that's not true either, because what I can do is I can kind of, that's not a very good graph. All right, just because the horizontal asymptote is 2, I can still cross it just as long as when I go out towards infinity, I approach it. So that doesn't have to be true, because here I did cross it. That's allowed. Okay, that is allowed. F of 2 is undefined. That means when x equals 2, we're not going to get a point. We can have a point. That's okay. So that's not necessarily true, because it says which of the following must be true. Okay. Here it says as x approaches 2, the curve has to go up towards infinity. That's not true. It doesn't have to do that. But this one is true. As I go out further on my x-axis towards infinity, the curve has to get closer and closer and closer to 2. So this is the definition of an HA. All right, as you go out towards positive infinity or negative infinity, your y values have to approach 2 if that really is a horizontal asymptote. So letter E is the correct choice. And that's it for that note card. Hopefully it makes sense. Just let me know if you have any questions.